Okay, I believe we're live. Hello, everyone. My name's Aoi Mundy, and I'm the head of partner strategy at NTT Research. And today I'm here with Dr. Logan Wright and Dr. Tatsuhiro Onodera. Logan and Hiro are research scientists at the NTT Research Physics and Information Lab. And so they are also visiting researchers at Peter McMahon's lab at the School of Applied and Engineering Physics at Cornell. So today we set aside some time to have a discussion with Hiro and Logan, where we're going to explore a little bit about how their expertise and some good old, garage innovation really help develop a novel concept where you can just kind of think about turning anything into a fast, energy efficient computer that may be able to handle some of the most complex inference tasks facing neural networks today. So Hiro and Logan are co-lead authors on a recent paper out of Nature, Deep Physical Neural Networks Trained with Backpropagation. And they share that authorship with 5 other researchers from Cornell. So we'll start this off first. If I could just ask Logan and Hiro kind of to start off the conversation, maybe you could provide us with an overview of the Nature paper itself, and maybe introduce us to this new idea of physical neural networks. Over to you.
Yeah, so basically what we've done in this work is figure out how to make deep learning, which is a mathematical algorithm, into a sort of a physical algorithm or a physical procedure. So I'm going to try and explain how things work. But I first want to just kind of say, like, this is really a early stage research. We think it's really fun. We think it's really neat. But it's not something that there are near-term applications of. We probably need a few years to figure out where it's definitely going to be useful. But hopefully towards the end of the discussion, we can talk about where it's plausibly going to be useful. So as the graphic shows here, this is the first figure of the paper. Conventional deep neural networks operate by using what are called layers to process information sequentially. For example, an image will be sent into a neural network, and a sequence of layers will learn how to perform different steps of a complex calculation. Like the example we're showing here is the neural network is being tasked with the computation or the task of figuring out what handwritten digit is being displayed in the image. And of course, we can all pinpoint that the image is of an 8, but the neural network needs to do a large number of operations on that image before it can figure out that same bit of information. In deep learning, the algorithm that people use to, learn to figure out the parameters and figure out the mathematical quantities that go into this neural network algorithm is called backpropagation. And backpropagation has been very, very successful in allowing people to discover these parameters or learn these parameters very efficiently. So one of the key things that enabled our work was to be able to figure out how to apply that to physical systems. So what the bottom part of this graphic shows are some of the different physical systems we've used to make physical neural networks. So imagine, if you will, that there's some billiard balls, on a table here, and the table is the gray slab, and the billiard balls are these colored circles. You could imagine performing a computation by encoding data that you want to process in forces that you apply to the red billiard balls. And you could read out the result of that computation by looking at the position of the blue billiard balls after you've hit those red billiard balls. And you can change the way the system evolves, or in effect, the computation that the system performs, by manipulating the position of the billiard balls that are shown in orange there. And in general, any physical system that we can adjust or control can, in some sense, provide a controllable computation. Whether it's the position of billiard balls, whether it's voltages that we apply to an analog circuit, or stresses or geometry that we change in a mechanical system. Physical systems, when they evolve, perform computations, And one of the key things that we've identified is that we can, in the same fashion as people use deep neural networks and deep learning, use physical systems to perform computation, even when they weren't nominally designed for that or where they don't have a specific structure in place.
So when did you guys start the research, and kind of what led to this idea of physical neural networks?
Yeah, so I'll take this question then. So we started this research actually in the fall of 2019. That's roughly when Logan and I joined NTT Research. And because our expertise is in the specific domain of optical system, and in fact, nonlinear optical system, our goal started out with trying to build physical neural networks out of nonlinear optics. So nonlinear optics is a particular kind of devices that allows you to say like create new colors of light, for example, and that's what we wanted to focus on. And the research started out basically building a physical neural network in the lab. So we used something called second harmonic generation to build it in the lab. And the plan initially was to have what we call training and simulation. So we'll have a simulation of that setup, and we would train or try to figure out how to utilize that setup to do machine learning in a digital computer and sort of like load up the parameters that we found in experiment. And that was basically the plan all along. And when we did that, we were very happy initially because simulation showed that the machine learning would work very well. However, we found that in experiment, the experiment and the simulation just didn't match very well. So this was actually a big problem for us in the research project. This was maybe around February. Fortunately, around one of the group meetings where we're discussing some ideas, Logan had this idea of PhysicsAware Training, which allowed us to figure out a way to train the physical neural networks with some digital system in situ. So what that means is to say you're not just sitting on a computer training it for like say 10 hours and then moving it to the physical setup, but rather in situ. So you're using both the physical system and the digital computer together, and that allowed us to basically get over this big hump. Once we got over this big hump, then we just realized, oh, this idea is very general. It's not limited to optics, even though that's our domain of expertise. And we kind of decided to demonstrate two other physical systems, which is the electronic physical system as well as the speaker system. One big part of this that I've sort of not mentioned in this particular exposition of the work is COVID, because COVID happened around March 2020, I believe. It's been a long time. And that drastically sort of shifted a lot of how our research was conducted. So here I have some slides which I show for entertainment. This happened right around March 18, where there was some lockdown instantiated. And we frantically had to get the sort of networking because you need to have very stable wired internet. And there was a lot of frantic sort of panic in trying to get the whole setup automated. And by automation, what we actually mean is like we actually was able to control the physical setup from the comfort of the home. In fact, I was primarily in the optical setup, so I was just sitting at home programming Python to determine or to build our physical neural network. And a good part of that, as you know, when you want to build anything, you have to see it. So we actually installed some security cameras that actually can move around as well, pan around to see our setup to sort of debug what's going on in the setup. Um, it also actually sort of shaped a lot of the other two physical setups that I mentioned briefly. So, in fact, the electronic PNN and the speaker PNN were very garage innovation, as Al pointed out, and that's because we were constrained by COVID. And so, as you can see, we actually have this PNN coexisting with Logan's dog over here, and that actually caused us some pain as well because he was basically interfering with the physical neural network. And here on the right, we see some speakers, which is also very friendly. So basically, Martin went to one of the speaker stores, I think some used store, bought some speakers, tore it apart, and used that to build a physical system.
So I'm just wondering, with these physical systems, what about noise, right? I would imagine, you had the dog in the environment, things like that. I saw the optical table was that on a floating optical table. Is this something that for physical systems and physical neural nets, I guess there's maybe potential of environmental noise, being a factor in the whole computation process, I'd imagine.
Yeah, do you want to take that one, Logan? It's up to you.
Yeah, sure, I can respond to that. So one of the nice things about this physics-aware training is that over the course of training, we tend to sample the natural fluctuations that take place in the environment. So in some sense, the physical system learns how to perform computation despite the noise that exists in the real world. So obviously, if there's like a catastrophic thing, like my dog comes by and its tail like knocks it off the table, that's not it's not robust to that. It can't survive that. But just things that are normally happening in the environment, like for example um, in our lab, there's a sort of temperature fluctuation that happens over the course of 24 hours and sometimes over half an hour. That thing, the physics-aware training can discover an algorithm that is automatically robust to that types of noise. So to get a little bit technical, we like to think about the parameters find a noise resilient manifold on which to perform the computation. Or if anyone knows about the concept in quantum computing, we think about it as a little bit analogous to a decoherence-free subspace.
Interesting. Okay. So, in the paper, when I was reading it, it looked like I was kind of expecting it. It looks like maybe there's a forecast there of these hybrid systems, right? Whether it's an in silico or whether it's in situ, right? And I think you referred to that in the paper. And so, are there ideas like for these? First of all, did I get that right? And if so, if it's a hybrid system, what might lend itself more to a mechanical approach versus an in silico approach?
Right. So I think there's sort of two distinctions here that maybe I wanna point out, which is that in silico training and in situ training, and that's sort of very specific to basically how you teach the neural network to sort of perform the task it wants to do. And you can do it in two ways. In silico, referring to basically the fact that you get your simulations and your experiment to match so well that you never interface with the experiment and you just train it on a computer. So like your digital simulation can perfectly emulate it, so you can use that to train. In situ training just means that you're going to utilize both the physical system and your digital computer to kind of work together to figure out how to make it do what you want it to do. And you might be right, and I'll sort of question if the digital computer is being used for the training, then what's the point of the physical system? Like, but and this is a good question, and I just want to sort of answer that now. And it's that in machine learning, there's two phases, which is training, which is to figure out how to do the task you want, and then there's inference, which is to feed it new data. So in the case of say Siri, what happens there when you try to use machine learning is Apple has first spent a lot of money to train that neural network to respond to the speeches you give it. And in inference, you don't need to train anymore. You're just using that neural network that's been trained and using it many, many times with different, whatever the billions of people around the world are telling Siri. So that's the subtlety here in silico and in situ. Now, as you pointed out, Al, there's also this thing called hybrid neural network. And that is to say that in inference mode, like when you use a neural network that has both digital as well as physical components. So one way you can think about this is um, suppose we had a neural network that had some digital processing at the start to sort of pre-process the data, and then you feed it to a physical system, like an optical system, and that optical system does the final part of computation. So here, it's a hybrid neural network. And from our perspective, Logan and I, as well as the folks at Cornell, we think that in the near term, like say 5 to 15 years, or 0 to 15 more exactly, we think the hybrid approaches are probably going to be the most promising way to go. And that's because, as you know, digital computers are very flexible, right? Like you can use it to watch Netflix and to email. And that flexibility essentially is very useful for you to help leverage the use of physical neural networks. So what you can have is a hybrid neural network where you have digital parts and physical parts, and by training them together, the digital parts can basically help figure out how to best leverage the physical part. It can even like offload the parts that has trouble with to the physical, and the part that the physical has trouble with will go to the digital. So that's what we think has the sort of most potential going forward. And as Logan, I think, will mention shortly, smart sensors is definitely sort of in this vein of like having some parts of it done in the physical domain and then offloading it to digital.
Yeah, before we move into smart sensors, in the paper, and I was trying to understand it better, where you guys were introducing the physics-aware training kind of an idea, and you had mentioned that it's a significant enabler, right, for these hybrid systems. And could you expand a little bit more on that, on what you mean?
Okay, so with any system, with any neural network, be it physical or just artificial neural networks, you need to train it for it to figure out how to do the task. One way to think about it is when a baby's born, it can't play chess. You need to teach it how to play chess, and that's the same for both kinds of neural networks. And the way you do that typically is by feeding it data. So you kind of show them an image of 8 and tell them this is an 8. So you give them both the labels as well as the input data. And you repeatedly, many times, feed this to the neural network to train it. And training can be done in many ways, and many different algorithms have been developed by the community, such as sort of genetic algorithm, which follows more like an evolutionary framework, or backpropagation algorithm. And so backpropagation is the one that's most preferred when it comes to deep learning, and that's because it basically finds the parameter in the least amount of time at a high level. And what physics-aware training does is it's an in situ backpropagation algorithm. So what that means is that it allows you to apply the backpropagation algorithm in situ, and that's to say that you're sort of interfacing with the physical setup constantly. Um, and it's kind of technical, so I probably don't want to go into it in too much detail. But we basically separate out the training process into two parts, and there's this thing called the forward pass. So in the forward pass, we're actually using the physical system itself, so it's aware of the noise, it's aware of all the condition that it's in, and then the backward pass, sort of when you take the gradients, which is to figure out what the best direction it is in, we use the simulation instead. So we're kind of using the simulation and the physical setup at the same time, and that's physics-aware training.
Got it. Makes sense. Makes sense. It sounds like Logan may be having some issues with audio. Logan, would you be able to expand a little bit on, the paper talked a little bit about possible applications in the future and potential sensors, things like that, and maybe like even the nanoparticles. Could you expand a little bit on what you were referring to in the paper?
Yeah, so because these are physical systems that are performing computation in a physical domain that is not digital electronics, it's sort of a pretty obvious thing to think about doing computation on data that isn't in the digital electronic domain. So it doesn't come out of like a memory or some hard drive or something like that, but is actually coming from the real world. So for example, a natural thing would be an optical physical neural network could, instead of processing images that are stored on your hard drive, it could actually process photons that are being scattered by an object. And this is something we're actually working on right now. Or you could imagine like a mechanical PNN that would respond like a microphone, but like a smart microphone that could respond, for example, to specific words that it hears. And by processing data that is in this sort of ambient world or that is in this different physical domain, there are a lot of advantages that you can get because you don't get the added noise that you would normally get in converting from acoustic to electronic, or from going from optical to electronic. Usually there's a lot of bandwidth constraint and added noise and going from the real physical analog world into the digital world. So that's probably a domain where we think we're going to have a lot of success because there's no alternative, right? There's digital electronics fundamentally cannot do computation outside the domain of digital electronics. So as far as like near-term applications, maybe in the next 5 or 10 years, smart sensors based on PNNs is what we're pretty optimistic about.
And you think that's translatable all the way down into nanoparticles as well?
Sorry, could you repeat the question, Al?
Yeah. Do you think that's translatable, down into the nanospace with nanoparticles as well?
Oh, right. So very often people want to design nano devices or things like nanoparticles that exhibit some functionality. right? So you put a nanoparticle someplace in the body, and it's going to interact with a specific protein or a specific molecule and mediate some kind of process. But designing a nanoparticle that takes on some complex functionality, you can almost frame that complex functionality in a physical setting as performing a computation, right? Really, computation is just some complex functionality of a physical system. We think about it as disconnected from the physical domain, but really it's just a complex functionality. So in the same sense that you could train a deep neural network to learn a mathematical functionality or a digital data functionality, you can think about designing complex nanomachines whose chemical or mechanical functionality is learned in the same way that deep learning is used to learn functionality of deep neural networks. So like just to give an example, you might design the shape and the chemical composition of a nanoparticle so that when it comes in contact with some protein you care about, it'll emit light. Is a natural thing to think about. We're not experts in nanoparticles or in nano machines, but it's a pretty obvious thing even for us.
Great, thanks. I'm watching the time, and we have a couple questions that came in. I'm not sure if you guys can see them on the speaker section. I have a couple questions myself yet, but maybe you want to get a couple from the audience. So there's one here. Are you guys able to see it? I'll read it, but are you able to see the question on the speaker slide? Okay, great. Yeah, so what would be the equivalent architectures in a traditional neural network for the physical networks you built? The simple billiard ball example reminds me a lot, for example, of recurrent reservoir computing with sparse random connectivity.
Okay, so maybe I'll take this one. So in terms of the equivalent architecture for a traditional neural network, it definitely depends on the physical system you use. So for concreteness, I think for the billiard ball one, I think it's you would think about it as simulating the classical equations of motion and sort of figuring out how the map from input to output is. In fact, we actually tried doing the billiard ball in the lab. This is one of the possible physical systems that we wanted to try to make a physical neural network on. One thing that we found is that it was very hard to make it a physical neural network and to train it with backpropagation because of how sort of spiky the input output behavior is. One way you can think about it is if the ball misses the other ball, then the output changes completely. And we found that was very hard to gradient descend on. And you mentioned recurrent reservoir computing with sparse random connectivity. So I think those systems are much more reminiscent, perhaps not with random connectivity, to the kinds of system we've been exploring in simulation. So if you have a lot of coupled oscillators together and they're coupled in some ways, then what you have is a recurrent neural network in time, where basically you have an ODE of the oscillators, and in that setting you can actually create quite powerful physical neural networks because you can basically engineer the connectivity between the oscillators and then use that to perform machine learning. And a lot of this is connected to the field of neural ODEs. And if you're interested in this, check out the supplementary material where we do some fashion MNIST with this physical system. Yeah, this is a very technical question, so I kind of went into a more technical answer.
Yeah. And there's a follow-up question. I think you've already touched on a little bit, but the connected question would be: are there architectures in which your physical backpropagation can run that are tricky for digital networks? And again, reservoirs come to mind.
Do you want to take this one, Logan?
Sure, I can answer this. So this is a pretty technical question. I do want to first start by commenting for specialists, a common thing that they confuse what we've done with is reservoir computing, which is a similar approach in which you take some physical system that you don't train, that you don't adjust anything about, and you use it to try to perform machine learning. We are not doing reservoir computing. In fact, in the supplementary material to the paper, which is freely available, we show that we get actually vastly superior performance. And the reason is that we actually adjust physical parameters. So it's not like we don't have sparse random connectivity. We actually have trained connectivity in these physical neural networks. So just like deep neural networks consist of trained layers, we have trained physical systems. As far as what are settings in which our physical backpropagation can run that are tricky for digital neural networks, this is a somewhat subtle question to answer because the nature of the backpropagation we do is actually digital backpropagation. We have a digital simulation for the physical system, and we do autograd to backpropagate through that simulation. And the forward pass is through the physical system. So in some sense, there's no setting in which these two things are going to be divergent because they're mathematically identical. Now, on the forward path, there are absolutely many circumstances in which it would be very, very challenging for a digital computer to simulate that system, right? Because it's a very complicated system that would require a supercomputer to simulate. So there's a potential for a very, very large speed up in the forward path being performed by the physical system. But currently, the backward path is performed in a digital computer, so they're sort of mathematically identical. In the future, we're working on it now, where we have ways of performing the backward pass also using the physical system. And it's relatively obvious how to do that if you sort of think about it for a few minutes. But in short, with the current version, the answer is that because they're the same, there's no real example.
Great. In the last couple of seconds or minutes that we have here, you already touched on it kind of in the future. Is there any really quick sound bites you can give us of what you guys are thinking for the next year or so?
Yeah, so one of the biggest things that we're trying to understand is, and I think this is a good thing to close on because it emphasizes how early the research is at, is what physical systems are good for performing computation? What physical systems are good as physical neural networks? What are the characteristics of, for example, the connectivity between the different degrees of freedom? Are fluid systems better, or mechanical systems better, or optical systems better? And what are the conditions for them to be better? These are deep theoretical questions that we're trying to understand and then translate into new designs for physical neural networks that might be scalable. The other thing that I mentioned before was smart sensor PNNs. We're actively working on that right now. And then the last thing I'll maybe just mention is that we're also bringing in what I would call weak quantum effects. So just looking at systems that are slightly quantum, that require a little bit of quantum mechanics to describe, we are pretty optimistic that we can leverage these kinds of systems, which are much easier to build than conventional quantum computers, for performing accelerated machine learning.
Okay, great. Well, with that, I believe we're out of time. I'd like to thank all of those who've joined on LinkedIn and to hear more about what Hiro and Logan's work has been up to within the NTT's Phi Lab, and to learn about potential possibilities of physical neural networks. Hiro and Logan, congratulations to you both on your authorship and on the Nature paper and co-authoring with the others. And thank you for sharing your thoughts with all of us today. And certainly for everybody out there to keep abreast of the latest happenings within the 3 labs at NTT, which is the Phi Lab, the Sys Lab, and the My Lab, be sure to check out nttresearch.com. And with that, thank you so much, everyone.